I'm Silviano Torres. I'm a fourth year physics undergraduate student, and my mentors are Miguel Cepeda, Dr. Lee, and my faculty advisor is Professor Silviano. And my research is on the optimization of X-ray scattering for the characterization of materials. Small angle X-ray scattering, or SAX, is an X-ray diffraction technique used to characterize materials such as proteins, DNA, and newly discovered materials like graphene. It is very important to be able to characterize materials because it allows scientists and engineers to understand them to our benefit. For instance, using biological materials like lipids and proteins as vehicles for drug delivery. The basic physics behind SAX is you have some material, an X-ray shot the material. A large majority of the X-ray transmits unaltered, but a small fraction interacts with the electrons of the material in a way to invoke a physical phenomenon known as scattering. And these scatter rays are picked up by a detector. At the same time, the transmitted beam is stopped from hitting the detector by a beam stop because due to its immense intensity, it would destroy the detector. And our detector provides these nice images or diffraction patterns where the bright spots represent areas of high intensity, where these scatter rays constructively interfere in accordance to Bragg's law. And please note that X-rays will scatter off all material due to electron interaction. And the focus of my research this past summer was to precisely define the incident X-ray beam, because by controlling the beam size and divergence through blade defining blades, And the basic setup behind SAX is you have your X-ray source, your defining blade, your sample, your beam stop, and detector. The X-ray is emitted from the source. The defining blade cuts the X-ray source in half, and it interacts with the sample, and of course stopped by the beam stop. And of course, scattering occurs, and it's picked up by the detector. Please note the entire setup is in vacuum so that the X-rays do not interact with the air molecules and scatter off, which would mess up our data collection, obviously. Here's a closer look at how the blade interacts with the incident X-ray beam. So initially, the beam and the blade are not interacting, and the profile of the beam looks something like this, where it's very similar to a Gaussian, which is the peak of the intensity. And then once the blade is moved into position, it cuts the beam in half and changes the intensity, as this graph illustrates. And the narrower the width of the intensity plot is, the more precise and defined it is. And to optimize SAX performance, we have to get a closer look at the interaction of the defining blade and the incident X-ray beam. Or in other words, what is physically happening at the instant the blade is interacting with the X-ray. And so a closer look at our blades is we have, two prototypes we have are the simple metal blade with a tapered edge, as you can see right there. And then our new hybrid blade, which we use the same basically prototype as before, but we add a single crystal blade on top, or a single crystal slit. And the aluminum blade, in this case I used aluminum for control, it was very bad at stopping parasitic scattering, which is the scattering that occurs when the blade intersects the beam. And the reason we want to decrease parasitic scattering is because it is detrimental to our data collection, because we are trying to understand the scattering from the material, not from the blade interacting with the X-ray. So it's bad, this is good. And, forgot to mention that the SAX setup has some fallacy to it. Since we're trying to get a better perspective of the entire incident X-ray beam interacting with the emitter, or the transmitted beam that comes out from it, we need a better perspective of or a better view of the entire beam. And we can't because of the beam. And this is where the expert probe comes in, where it has a better detector, and this is the basic setup. You have your X-ray source, your sample, the X-ray shot the sample, and it scatters, of course, when you pick up by the detector. The main reason we use this is because of the fixed array detector, which can withstand the high intensities that the previous SAX diffractometer could not take. And note that this setup is not in vacuum, which will bring about some errors or problems, issues that I will later discuss. And some factors that we take into account when choosing candidate blade materials. One is the X-ray attenuation, which is the ability for the material to stop the X-ray from penetrating through, which is correlated to the density. And of course, the smaller the X-ray attenuation, the better, because the smaller the X-ray attenuation, the less material it takes for the material, the less material it takes to stop the X-ray from penetrating. And we also bring into account, well, one of the factors is the strongest reflection angles, and what it basically is the angle at which the single crystal slit is placed on top of the tapered edge of the blade. And at certain angles, the crystal lattice will be aligned normal to the X-ray beam, in which it would actually reflect the entire beam that's in contact with it, which will be also detrimental to our data collection. So here's a closer look at our two prototypes, the aluminum blade, and in this case our hybrid blade with the germanium crystal active. The diffraction patterns that we saw from the Sachs diffractometer was that the scattering for the first prototype, the single blade with no single crystal on top, was really bad scattering, and for the hybrid blade, which is very, very extremely reduced, which is good. It's what we want. And here is the intensity plot of the parasitic scattering from the two prototype blades. This blue is the blue is the aluminum blade, and the red the hybrid blade. As you can see, the hybrid blade is magnitudes less, which means that it provides less scattering, which is exactly what we want. And just to note, this is where the blade comes in and cuts the beam. And here's the data that was provided from the Expert Pro. It did a job. It provided a good profile of the entire incident X-ray beam after it interacted with the blade. And the red line is the direct X-ray beam without the slit placed in contact with it, and the purple is with the slit placed. And as we expected, it's about half the width of the direct X-ray beam. Another thing we're looking for is the parasitic scattering, which we couldn't really find because of the great intensities the direct beam was in comparison to the scattering. And this is because, as I aforementioned, the scattering comes about from a small percentage of the X-ray interaction. And so, after looking furthermore, we saw that this might be some instance of scattering. We're not entirely sure because the entire setup was not placed in vacuum. So we are pretty sure that the X-rays were scattering off of the air molecules and messing with organic formation. And further data is being analyzed to figure out how we can enhance this setup so that we can get a better perspective of what our profile looks like. And my summer research has brought much insight into these X-ray diffraction techniques. The MRD Pro provided some good information and needs further investigation of the setup. And many candidate materials still need to be analyzed so that we can understand which is the best material for our purposes, or any other purpose that there might be for X-ray diffraction. And I plan on continuing my research in the fall and hopefully progressing to optimize its performance. And I would like to thank my administration, Dr. Bella, Dr. Rudy, my faculty advisor, Professor Silviano, and EUREKA, as well as the MRI for the research. Thank you.